Hello, my name is Katie Law, and I will be presenting our work, Learning to Detect Mobile Objects from LiDAR Scans Without Labels. Our work centers on 3D perception from point clouds, one of the key components of the self-driving application stack. Though there has been significant advancement thanks to machine learning techniques, training these large-scale models often requires collecting large quantities of labeled data, making it challenging to deploy at scale. Our work focused on trying to tackle object detection in a label-free manner. Why might we want this? Collecting a large quantity of 3D object labels required to train these detection models for self-driving is expensive, challenging, and labor-intensive. Furthermore, models trained from these curated datasets are often prone to domain shift. In order to deploy self-driving detection into all cities, we must have a way to either cheaply obtain these labels or slowly reduce our reliance on them. Let's take a step back to what information we do have, but was previously ignored. The reality of self-driving is that people tend to drive on the routes they have driven before, for example, routes to school, work, or shops. Even if you embark on a new route, it is highly likely you are following the footsteps of other drivers. This is a distinct opportunity. Past traversals of the same location, despite being unlabeled, will always be available. As people drive through the same route, we can get multiple past scans of the location, even at test time. This is distinct from traditional 3D perception, which basically treats each LiDAR scan as completely new. We start by exploring how to pull out the objects from repeated traversals systematically. Our key insight is that multiple traversals can provide sufficient hints to determine if a point is persistent over time or not. In this work, we want to know what points in the scan correspond to mobile foreground objects. To do so, for each point, we query into what it looks like in other traversals. You can imagine, if the points corresponding to persistent objects, it should look quite similar across different traversals. In contrast, it will look quite different if it is a mobile object, since we assume that the mobile objects move. To capture this, in each traversal, we compute the number of points within a neighborhood of the query point, resulting in n1 to n4 in this case. We then normalize point cloud counts across traversals to have a pseudo-distribution over 4 different traversals. If the query point belongs to a persistent background, such distribution should be quite close to the uniform distribution. We then define persistency point score based on this, which is essentially just the KL divergence between the pseudo-distribution and the uniform distribution. The higher the P2 score, the more likely the point is persistent. Here, we show a visualization on the P2 score, along with 2 of its corresponding past traversals. We can see that the mobile objects simply pop out from the background due to their low P2 scores. Let's show one example of how we pull out the C labels of mobile objects. We start from a LiDAR scan decorated by the P2 score computed from the repeated traversals. Next, we run graph clustering on the point graph defined using Euclidean and P2 similarity. From these clusters, we fit upright bounding boxes. And finally, we filter out common sense defying boxes to result in a number of bounding boxes that are potentially mobile objects. We compare these pseudo-labels with the true labels. One thing to bear in mind is that we do not use any human-annotated labels in the whole process to generate these boxes. For our complete method, we introduced self-training to iteratively refine the detections. At each iteration after the initial C labels, we use the predicted bounding boxes of new pseudo-labels, filter out background objects using P2 score, and train the next mobile object detector. We term our method MODEST, short form, Mobile Object Detection with Ephemerality and Self-Training. We confirm our findings qualitatively by looking at the detection results and the C labels. Surprisingly, training using the MODEST framework improves recall with each round of self-training. Quantitatively, we are surprised to find that it performs very well. In fact, it manages to surpass the out-domain supervised counterpart. This suggests MODEST can potentially solve detection for self-driving at scale. We also show performance of MODEST after various rounds of self-training, up to 40 rounds. Observe that using P2 filtering is key towards the strong performance of these mobile object detectors. Interested in learning more? Check out our release code and read our paper for additional details.